Yeah, so let's go over the daily two for today. And so I'm going to share the screen and get to my daily two, which is right here. And the first question is, which of the following is the unit for period? Period, if you recall the definition, it's the time it takes for one wave to pass a certain place, or the time for one cycle. Keyword there being time. So the correct response there is seconds. The correct response there is seconds, okay? And looking at my spreadsheet of responses for this, about 3/4, a little bit more had that. The most popular incorrect answer was 1/seconds, okay? That is actually the definition of hertz. A hertz is a 1/second, dimensionally. So 1/second is actually the unit for frequency. Seconds is the unit for period, all right? And then the second question was, a figure skater jumps up from the ice as part of her routine. What is her acceleration at the top of her flight in meters per second squared? And the answer is, doesn't have to be a figure skater, it can be anything in flight. The acceleration at the top of her flight, or on the way up, or on the way down, is always negative 9.8 meters per second squared. Okay. Success rate in this class of 80% for that. So still not where I'd like it to be, because I'd like it to be at least 90%. So I'm just going to keep on answering that, asking this question from time to time. The anytime anything is in flight, the acceleration is always negative 9.8 meters per second squared. At the top of her flight, the velocity is momentarily zero, but her acceleration is always negative 9.8. Okay, questions, comments on that? Well, all right, then what I'm going to do now is to go over the answers to Waves Worksheet 1. That which you submitted by the end of the day Friday to Schoology. I gave you 5 points for submitting that. All right. If you have yet to submit that, then get it in as soon as you possibly can, and you will, lose fewer late points. All right. So here it is. That which is what I call don't make waves. So the first one, the following terms, equilibrium position, that's the rest position, okay? The dashed line, crest, trough, and amplitude. Ooh, I forgot wavelength. Wavelength is the distance from crest to crest. I'll have to fix that. Wavelength is the distance from crest to crest. All right, so I guess I missed that on here. All right, definitions. Just straight out of the notes here. This is actually posted. I will fix the number 1, and this is actually posted in this week's folder as well. So I'm not going to read these definitions. You can access them yourself. And I did not correct yours. I did not correct it. I simply saw if you had answers. So I'm kind of putting that on you to see if did you get the correct definitions. Okay. All right, number 3, a wave generator produces 12 pulses in 3 seconds. What is the wave frequency? Frequency is defined as waves per second, or in this case, pulses per second. 12 divided by 3 is 4 hertz. 4 hertz. And then the period is the reciprocal of the frequency. Okay, period is the reciprocal of the frequency, and that's 1/4 hertz, and so that's 0.25 seconds for the period. All right. Any questions so far? Okay. Number 4, a wave train has frequency 5 hertz traveling at 2 meters per second. What is the wavelength? From V is equal to F lambda, divide out the frequency, okay? To get the lambda is equal to the speed divided by the frequency. 2 divided by 5, that's 0.4. And then hertz, recall hertz is a 1/seconds. So that 1/second, that second down there is going to cancel this second up here. And we'll have meters over 1 or just meters. So 0.4 meters for that. The period, once again, will be the reciprocal of the frequency. So 1/5 hertz, 1/5 hertz, and that's 0.2 seconds. All right. Questions, comments on that? Okay. Number 6, if they're out of phase, X is moving up while Y is moving down. All right. Next one, a pulse of amplitude 5 centimeters and a pulse of amplitude 8 centimeters travel in the same spring. They travel at the same speed. Speed is not affected by amplitude. Okay, amplitude, small wave, short wave, tall wave, doesn't matter. If it's traveling in the same spring, it's going to have the same speed. Okay. A pulse of 5 centimeters travels in a stretched slinky, while a pulse of 8 centimeters amplitude travels in a heavy spring. We can ignore the amplitudes because we know that that doesn't have any effect. So does the stretched slinky have a different speed than the heavy spring? And the answer to that is yes. The 8 centimeter pulse, which is in the heavy spring is harder to move. And if it's harder to move, which would qualify as a more dense medium, then the wave is going to travel slower than a pulse in a less dense or easier to move medium. Okay, such as in this case the stretched slinky. All right. Okay. Questions, comments so far? All right. Fixed end reflection comes back out of phase, and free end reflection comes back in phase. And I saw that in many cases. All right. All right. What I'd like to do now, before I go over the answer to this next one, I wanted to. All right. I wanted to show you a simulation of superposition once again. Okay, so I'm going to keep this screen. I'm just going to keep screen, and I have a thing in this good superposition simulation, and I don't think I have it loaded, so I'm just going to load it up like this. All right, and I found this. I've had this for years actually, and so what we have is a pulse of, I don't know if you can see those. If you look real carefully, there's a grid back here. There's a 2 amplitude pulse here and a 3 amplitude pulse here. And as I let them run, okay, so I have them run, they interfere, okay, and then they go right through each other and continue on their way, okay, and they're going to bounce and do it again. I'm just going to let this thing go. And so this is constructive interference, okay? And if I can pause it at just the right time, wow, nailed it, almost. The pulse, the 3 and the 2 add up to +1, okay? And so this is constructive interference, all right? Now, we do not see the individual pulses as they interfere. We only see their superposition, okay? All right, this would be an example of constructive interference. Now, if instead I have a pulse height of -2, they're going to destructively interfere. And if I show the individual pulses as they travel through one another, we see this, okay? And then while they're interfering, okay, the +3 and the -2 add up to a -1, all right? And so this is called destructive interference. We do not see their individual pulses, we only see their superposition. And then if I put the pulse heights as exactly the same, +3 and -3, and I let this thing run, there will be a time when, didn't do that right. I'll have to reverse the time a little bit, where they will completely, this is called total destructive interference, when they cancel each other out completely. And this will be the case if they have the same shape and the same amplitude, except one is positive and one is negative. Then they can totally destructively interfere. So this is superposition as well. Okay. All right. Now getting back to my Waves worksheet 1, which is, where was that? Is it here? Yeah. Waves worksheet 1. Now, as we look, here are the answers when they overlap. Notice each pulse is 3 units wide. Talk about the left-hand third. The left-hand third being +3 there, +1 there. That's going to add to a +4. The middle third, +3, +1, add to a +4. The right-hand third, +2, +2, also add to a +4. So while they overlap, okay, the spring or whatever's traveling through spring is going to momentarily look like this as they superpose, as they interfere. Okay, after they emerge from one another, this one will be traveling to the left over here. This one over here will be traveling to the right over here. Now let's go to this example. Okay, so now let's talk about thirds again. When they're completely overlapped, the left-hand third here is -2. This one is +1. -2, I'm sorry, -2, +3. -2, +3, add to a +1. Middle third, -1, +3, add to a +2. Right-hand third, -1, +2, add to a +1. So when they are completely overlapped, they would interfere to form this shape momentarily. Okay? So when I ask you to draw the superposition, okay, when the two pulses overlap, this is what I want you to draw. Some people put, they drew both pulses at the same place, but they didn't draw their superposition. Okay, this is when I ask you to draw their superposition, this is what I'm looking for. We do not see the individual pulses as they interfere with each other. We only see their superposition. So that's what you should sketch next time if you didn't do it this time. Okay? Okay, any questions? Questions for me? Yeah. All right. Well, then the next thing to go through are something called standing waves. Okay, now we're going to do a little, you guys can write this stuff down. I'm just going to keep the screen for a while, okay? So standing waves, I'm going to show you them in a minute, but these are produced. Let's do the writing first. Standing waves are produced by two waves of equal amplitudes and wavelengths traveling in opposite directions in the same medium. Okay, just kind of write that stuff down, and I'm going to show you this in a couple of different ways momentarily. All right. Produced by two waves of equal amplitudes and wavelengths traveling in opposite directions in the same medium. Just never mind about the stuff down here yet. Okay, never mind about that. I want to show you them first. So standing waves are produced by two waves of equal amplitude and wavelength traveling in opposite directions in the same medium. Okay. All right. Now, let's see, how do we want to do this? I think I'm going to go back to my simulations. Where was my simulations page? Oh, here it is. And I'm going to get to my simulation, my standing wave simulation. Okay, so I have this. All right, now I have, no, I'm going to hide one of them for now. So I have a wave that's traveling. Let's just let this thing run. So it's traveling to the left. And let's say that over on the left-hand side is a fixed end. All right, and that fixed end is going to reflect this wave out of phase. Okay, reflects it on the other side. Remember, fixed end reflection? So we're going to have another wave coming back like this. Okay, they're of equal amplitudes and wavelengths. So I have the blue wave traveling to the left and the green wave traveling to the right. And these two waves are going to interfere. Sometimes, if I could, oh, just missed. Sometimes the crest of one will match up to the crest of the other. Like, almost got it. Like, oops, wrong way. Like now. And a crest will add to give a double crest. The trough and the trough will add to give a double trough. And so their superposition would look like this in red. Okay? All right, now let's let this thing run. Actually, I'm going to step it. And another short time later, okay, now a crest is going to match up with the trough. And a crest matches up with a trough, and a crest matches up with a trough. And what we get is destructive interference. Not just destructive interference, but total destructive interference. Okay? Later, crest and crest will match up again. Trough and trough will match up again. And we get something like that again. Okay? All right? So as the waves continue to travel through each other, all right, they form their superposition looks like this. Now, we do not see the individual pulses or the individual waves. We only see their superposition. So you get a wave that does this, seemingly standing still, hence the name standing waves. Okay? Now remember, these are produced by two traveling waves that are traveling in opposite directions on the same spring. They have equal amplitudes and wavelengths, and they produce a wave that looks like the red. Okay? All right, so I'm going to stop this. Okay, and get back to our PowerPoint, which is where, I wonder. Oh, by the way, now that I'm thinking of it, I shared this thing that I called good superposition simulation. I scored the, I loaded this onto the this week's Schoology folder. So if you want to play around with these simulations like I'm doing, just go to this week's Schoology folder, and you will find this document in there. You can access these links and have some fun. Okay, all right. Getting to that later. Where is my? What am I trying to get to? Waves presentation. Yeah. So now alternating constructive interference and destructive interference produces a wave that seems to stand still. Okay, that seems to stand still. All right, and we're going to sketch this in a moment. But before I do that, I want to show this to you. So last Friday, I filmed this in my room, and I'd like to show this to you. Okay. All right. I want to full screen it if I can. All right, and then play it. Okay, so I'm going to produce a wave from my hand. The wave is going to go to the fixed end on the other side where it's attached to the board. It will be reflected. Question. Can you guys hear me talking? Give me a thumbs up if you can hear me talking. Okay, thank you. I'll get back to that. Full screen it. Get out of phase and interfere with the wave that I continue to send to the board. If I do it just right, a standing wave will be formed. Check it out. Notice there are places on the screen that don't move at all. That's the node. So the location where we'll write this stuff down in a minute, okay? The place that doesn't move is called a node. And you can kind of tell where they are. One of them is right about here, and one is right about there. Vertical line on the board between the two sliding board and the fixed board. Okay. There's another node about at the end of my desk. The maximum displacement, they're called anti-nodes. Okay. So if I do it just right, I can form a standing wave in the spring. Now, I'm going to form a wave that if you snapshot it, you'll see one crest and one trough. All right, like this, like that. So if you freeze frame it, you'll see one crest and one trough. I'm 4 meters away from the floor. If you're wondering what that was, I had a slinky that was in my marker tray, and this spring knocked it off. Okay, see the slinky there? All right. The vibrating, the heavy spring knocked it right off the chalk tray or the marker tray. So if you freeze frame it, you'll see one crest and one trough. And find 4 meters away from the core. Find 4 meters away from the core. Then the wavelength of this wave will be 4 meters. This is from the core, one crest. One crest, one trough in the 4 meter distance. Okay, if you freeze frame it, you can see one complete wave. One trough. Okay. Now I'm going to form a standing wave that has a wavelength and a half. So if you freeze frame it, you'll see 2 crests and a trough, or 2 troughs and a crest, depending on when you stop when you take the snapshot. Okay, you'll see 2 nodes between me and 4. It's the one I had at first. Right there. Yep. Okay, the node about right there and about right there. Notice I have a crest and a trough and then another crest. So a wave and a half. Now if you freeze frame it, there's a wave and a half between me and 4. So 2/3 of the way across will be the wavelength this way, 2/3 of 4 meters. Okay? Okay, I'm going to do this again. This time, I'm going to have 2 complete wavelengths between me and 4. So you'll see, if you snapshot it, you'll see 2 crests and 2 troughs. All right? I didn't actually realize this till later, but I didn't observe it carefully enough. There's actually 1, 2 and a half. So actually I missed the whole 2 wavelength and I went right to the 2 and a half. So there's 1, 2, 3, 4 nodes in here. Okay, so I didn't observe it carefully enough. This is actually 2 and a half wavelengths. Okay, but you get the idea. Yeah. 3 nodes. 4 actually. So if I have 2 complete waves between me and 4, and there's 4 meters between me and the fixed end, that means each wave had a wavelength of 2 meters. Notice that as I generate these different waves, the wavelength of the traveling waves is decreasing. Okay. Now, so I'm going to hold off on that for a minute. Okay, I'm going to escape out of here. Now let's go back into our waves presentation. I'm going to actually stop sharing because I want to draw this with you. So I'm going to put it on my camera down here. Yeah. Oops. Didn't have it in position. Sorry. So I'm going to have a fixed end there, and I'd like to draw 1, 2 waves. Okay. Fixed end here, fixed end here. So draw this with me. Okay. 1 wave, 2 waves. Okay. And then when it bounces back, if I do it just right, this is a little tricky to draw. Okay. It's going to come back here. Okay. I didn't get this part done very well. Let me do a better job of this part. Maybe like that. Yeah. Okay. And so these, the wave, I'm going to have you draw that, and then I'm going to show you what's going on. Okay. So we get, if you get something that looks like this. Now here's what's really happening. A wave is coming down here, hitting this fixed end, bouncing back out of phase. So it's on the other side. So it goes like this. Gets to here. Get my finger out of the way. Get my hand out of the way. Gets to here. Reflects, fixed end reflection, out of phase. So if it reflects like that. Out of phase reflection, reflects like that. Out of phase reflection, reflects like that. And back and forth and back and forth and back and forth. And if the waves are just the right length to fit between these fixed ends perfectly, there it will form a standing wave. And that's just another way of kind of explaining standing waves. But it ends up looking like this. Now, the places on the wave that don't, the places on the spring that don't move at all are called a node. Okay? The places of maximal displacement are called antinodes. Okay? So node and antinode, label. All right? Now, keep in mind, do I have a highlighter handy? Keep in mind that this is not what we would see if we froze the camera. If we froze the camera, we would only see one of those, okay? You see that kind of highlighted in yellow there? But over time, this is what the spring does, okay? In this case, there are 3 nodes and 4 antinodes between the fixed ends, okay? So this is a standing wave, all right? Okay, questions, comments? All right, one more thing to see in that little video that I made. Full screen it. There it goes. I have to oscillate my hand more frequently. So the frequencies, each wave had a wavelength of 2 meters. Notice that as I generate these different waves, the wavelength of the traveling waves is decreasing. Okay? Now to generate those, I have to oscillate my hand more frequently. So the frequency of the waves is increasing, while the wavelength is decreasing. That makes sense from V equals F lambda, that to have a shorter wavelength that must increase the frequency. All right? So these are different standing waves that can be formed in a string of fixed length. Okay? Standing waves. All right, getting back to here now. So here was a standing wave that I generated first that consisted of 1 crest and 1 trough, okay, like that. Perhaps up here I should have only highlighted one of the waves. I probably should have only highlighted one of them. So if this was 4 meters between fixed ends, like my hand and the bracket on the board, then the wavelength of this wave would be 4 meters. If I increased it like this, now the wavelength is only 2 meters, halfway across. To generate this one, I would have to oscillate my hand much greater, okay? And this gets back to V is equal to F lambda. In the same spring, the speed is going to be the same. Remember, wavelength doesn't affect the speed. So the speed of transmission here and the speed of transmission here are equal because it's the same spring. But what changes is the frequency and wavelength. If the wavelength decreases, then the frequency must increase to compensate. That's why to generate this wave, the frequency that I had to oscillate my hand had to increase, okay? So within the same medium, the speed remains the same. And if I change the frequency, the wavelength will change accordingly, okay? And vice versa. All right? Okay, one more thing to note about standing waves. And that is, I want to get back to my simulation to show you this. Oops. I can't minimize it while I'm recording. Okay, so I'm going to share. Oh yeah, that's how I do it. All right, and where's my simulation? Let's see. Here. So now, as this thing is going through and running, okay, now I cannot see the individual pulses. I only see their superposition. So what if I wanted to find the wavelength of the waves that were creating these standing waves? What if I wanted to find the wavelength of them? I can't see the individual waves. I can only see their overall effect. How could I find the wavelength, the wavelength of the blue wave? Well, there's a way to do that. Let me stop it at the right time. Okay, almost. Notice that the distance between the nodes, the distance between the nodes remains constant as this thing runs. It's in this case from 0 to 0.5. So the distance between the nodes is 0.5, right? Okay. Notice if I pause it just at the right time, just about got it right that time. Notice that the wavelength of the wave is exactly doubled that. Okay, exactly doubled, and that's also the wavelength of the reflected waves. Okay, so we don't need to see the individual waves. We can find the wavelength by just measuring the distance between the nodes and doubling it. And you can do that. If while I was oscillating that spring in my room, I could have had one of you in a normal year come up and measure the distance between the nodes with a meter stick, right? And that would be the distance of the traveling waves that were traveling through the spring. All right. We are going to take advantage of this later when we talk about musical instruments, stringed instruments such as guitars and violins, wind instruments such as trumpets and flutes. Okay, because this is the mechanism by which music is produced. Okay, no standing waves, no music. That would be bad. Okay, so that's standing waves. And again, if you want to play around with those simulations, the links to them are loaded on the website. Okay. Any questions? All right. Well, what's next? Oh, I wanted to show you another video of my wave tanks. And before we get into, I want to show you, this is going to, okay, I'm just going to show you another video. All right. And this is from my wave tank. So I'm going to share the screen again. Pardon me for hogging it. I'm kind of done with this for now. I'm kind of done with this for now. I'll get some things in the way here that you guys can't see. And let's see. Okay, I guess I'll have to access it like this. Wave refraction. All right. Wave refraction. It's another YouTube thing that I made. And I just want to play this for you. I was going to have you watch it yesterday, but there were some. Okay. I'm not. There were some points that I should have made in this video that I did not. All right, and you need it to finish Waves Worksheet 2. And so I thought I would just take 5 minutes and play the video, and then say that which I need to say. So anyway, let's just view this. Set up to demonstrate refraction of a wave. Refraction of waves occur when they travel from one medium into a different medium. And I have set up the wave tank to have different depths of water. Over here is the wave tank just like it was before. But over here, I have put a glass plate into the tank that's being supported by some glass blocks that will create a region of shallower water. Okay, so the waves are going to travel from deep water into shallow water. Okay, and when they do so, they will change speed. Remember, the speed of a wave depends on the medium through which it travels. And waves can travel through deep water faster than they can travel through shallow water. Okay, so when the waves encounter this barrier and travel onto and into the shallow water, they will slow down. Okay, and when they do, they will actually change their wavelength. And as an analogy to this, picture an army boot camp and an obstacle course, and where a line of men, say, are released by a drill sergeant or whatever, and they run across a field. And in that, they can run really fast across the field, so they run fast across the field, and then they get to a set of tires, and they have to go through a set of tires with their feet. And when they do so, they're going to slow down, because obviously they're going to slow down in the tire thing. They're going to run slower through there than they can across the straight field. And if I have a set of guys, like 10 yards apart in the field, when they get to the tires, the distance between them will decrease. because first guy's going to hit the tires, go through them, but they're going to slow down. The second guy's going to catch up, and so forth and so on. So the distance between them will decrease. Well, the same thing happens with waves. If I send a wave from deep water into shallow water, and the first wave front is going to strike the barrier, it's going to get into the shallow water and slow down, while the wave coming behind it is still in the deep water and traveling quickly and more quickly. And so it will sort of catch up, if you will, and to the wave in the barrier. And so if I have a set wavelength in the deep water, say of the distance perhaps between these two pencils, if this is the wavelength, okay, when the first wave strikes the barrier, it's going to slow down. This one's going to kind of catch up to it a little bit, and the wavelength in the shallow water is going to be smaller, just like the distance between the men in that obstacle course analogy. Okay, so see if you can tell how the waves strike that barrier and slow down. Okay, all right. Now that's not actually what refraction is, but refraction is due to this. So we can see the change of speed. If you observe very carefully, one wavefront as it travels onto the glass plate, perhaps you can see it slow down. Okay, and that's interesting, but we can make it even more interesting by angling the glass plate like this. Okay, now the waves as they pass into the barrier, different parts of the wavefront will strike the barrier at different times. Will enter the shallow water at different times. This part will enter the shallow water first and slow down, while this part is still traveling fast. And so if this part slows down while this part is traveling fast, the whole wavefront will change direction. Okay, so see if you can observe that. This will be the ray of propagation. And you can see the wave change direction from, say, going in this direction within the deep water to more in this direction in the shallow water. Okay, this is refraction. Okay, so refraction is, and I'm going to say it again in a moment, the bending of a wave as it enters a new medium. Okay, now this is due, and I'm going to repeat myself in the video too. This is because the speed changes, but there's a very fundamental point that I want to make here. And I want to go back to the men running across the field. So you got this obstacle course where drill sergeant's letting one guy go at a time. And as you're in a tower over this field watching this obstacle course, there's going to be like 10 yards between each guy. So you got a line of guys. If you take a snapshot, you see guy, 10 yards apart. Then when they enter that tire thing, they have to go through, 1 foot in each tire and try to get through without falling down. Let's say they do get through it without falling down, but they're naturally going to slow down as they are in the tires. But the number of men is not going to change. If 10 guys run across the field, 10 guys go through the tire thing, and they emerge on the other side and run across another field or whatever. The number of men doesn't change. Okay, so now in my water tank analogy, the number of guys is analogous to the number of waves or the frequency. So it's a real important point that the frequency of a wave doesn't change. Okay, what does change, and this goes back to V equals F lambda. If the speed changes, then the wavelength changes. If the speed decreases, then the wavelength decreases. But it's real important to know that the frequency stays constant. This is going to be a theme. Once generated, this is the first time of many that I'm going to state this. Once generated, the frequency of a wave never changes. Okay? If something else changes, like the speed, then the wavelength will change to compensate, but the frequency remains the same. Okay? Because you can't have a guy in my obstacle course analogy. A guy doesn't just poof into nothing or poof out of nothing. Okay, a wave doesn't just disappear at the boundary, or up here out of nothing as it goes through the boundary. The number of waves remains constant. Okay, a speed change will result in a wavelength change. Okay, that's a key point. Bending of a wave as it enters a new medium. Okay, and it's completely due to a change in speed. This part of the wavefront strikes it and slows down, while this part is still moving fast. So the whole thing changes direction because the speed changes from one medium into another. You can see that observed right there. The more severe the speed change, the more bending. Actually, maybe you can see the wavelength difference. If I back this up, the windows are in the way. So let me see if I can just stop this at the right time. Right there. The more severe. If you look, here's the wavelength in the deep water. Here's the wavelength in the shallow water. And you can see the difference. Okay, fast speed, larger wavelength. Slower speed, smaller wavelength. And because different parts of the wavefront slow down at different times, the whole wave changes direction. Speed change, the more bending it will occur. Okay. This is how lenses bend light and focus light. We will address that in a later unit. So this is refraction. It's the bending of a wave due to a change in speed. All right, I'm gonna start writing some stuff down here. So I'm gonna stop sharing and I'm gonna go to my thing here. And so refraction. The bending of a wave, as it enters a new medium, okay? And starred point, because this is important, it's due to a change in speed. Because the speed changes, the direction changes. Okay? I just thought of another analogy I can show you. We can talk about this. Let's say that my computer mouse is a car. Actually, make it smaller. My eraser is a car. Okay? And this car is going to go from a region of concrete where it has good grip into sand where it has less grip. Okay? So now if the car enters, if the driver's side tire and the passenger side tire enter the sand at the same time, okay, the car slows down, but it doesn't change direction. You know, we're not going to wipe out or something like that. Let's say it doesn't wipe out, it just slows down. So it slows down, but it doesn't change direction. Okay. Well, what happens if it hits it at an angle like this? If it enters the sand at an angle, the driver's side wheel will enter the sand first and slow down. The passenger side tire is still on the concrete, it still has grip. So what's going to happen to the car? The whole thing is going to change direction. Again, it doesn't wipe out, but it changes direction. As that one slows down, that one goes up. And so it changes direction going from here to something like that. From going from here to something like that, as the car goes from one surface to another. Okay. All right. Same type of thing in water. So if I have a deep water region and a shallow water region, deep water, it can travel fast. Shallow water, it can travel slow. If I talk about a wavefront like this, as the wavefront travels towards the slower medium, I didn't do that one very well, did I? A little bit better. Okay, this part of the wavefront is going to hit the shallow water first and slow down. Okay, this part of the region is still going to be going fast. So what you have is this part that's going to be like there, but this part, this won't be here anymore because it slows down. Now it's only about here. Okay, so the whole wave is going to do this. And by the time the wave gets into the other medium, it is now the ray of propagation would be like this, okay? And the wavelength here and the wavelength there are different, okay? Lambda 1 being larger than lambda 2. Once again, we can explain this by V is equal to F lambda. If the frequency stays the same, then a decrease in speed is going to cause a corresponding decrease in wavelength. Okay, all right. So let me zoom out, try to get that whole page in there. Got a request to show the top again. All right. Okay. All right, that's refraction. And that plays a really important role in light, as I mentioned about lenses. Okay. And in water. All right. Okay. Questions, comments on that? All right, tomorrow I'm going to have you guys watch another couple of videos that I made in my wave tank. One on, let's see here, one on diffraction, which is the bending of waves around corners, and then something else called two-point interference, which honestly I will never test you on, but it's a super interesting thing that I'm just going to show you because it's only like a 5-minute video, and I'm going to show you some stuff on Wednesdays. All right, and then there will be Waves Worksheet 2, which after now you can complete, and I'm going to have that due on Friday. Okay, submit to Schoology by Friday. All right, and that really completes our general wave unit. All right, and now I'd like to head into sound. Okay, so what do I have here? What have we done? I believe we have until 2:05, right? 2 o'clock. I have until 2 o'clock. All right, so 25. I'm pretty much going to take the rest of the time. All right, and get as far as I can into our sound unit. So I have another, let's see, sound presentation. Where is it? It's right here. And I'm going to start this. But before I do that, I want to do this. Oh gosh. So, okay. Excuse me for just a moment. Oh gosh, what's going on? Oh, I know what I did. Okay. All right. All right, so I'm going to take the screen and we're going to write some stuff down about sound, okay? And I have some demonstrations. I'm not sure how far into it I'm going to get, but we'll find out together. So let's see. I want to do my sound presentation, right? And I want to start this. Well, that stuff is in the way. Slideshow. Front start. All right. Sorry that took so long. Sound. Okay. Now, if you were in my room, and I really, really wish you were, the first thing we would do are experiments with the tuning fork. Okay. Now, let me show you what a tuning fork is. I'm going to stop sharing. Okay. This is a tuning fork. All right. You hold it on this side, and then you strike it on this end, like something soft, like a book or an eraser. Okay. Probably can't hear that. I don't know where the microphone is in here, but you put up to here, you can hear a nice pure tone from this. Okay. Now, what I would have you guys do is to do some things like place it on some things like the, well, various things, but you can hear that. You hear that? Maybe try it on my ring stand. Oh yeah. Sounds like a doorbell. Okay. Maybe on the tabletop. Or if you put it on your ear, tickles. I would love if you were here to do this stuff in my room. Okay, you can feed you can do some fun stuff with this, right? I don't know if this will work or not. This is not one of my better tuning forks, but it's just the one I grabbed. Hold on just a minute. I have a glass of water here. Okay. And let's see here. Put on a sheet of paper. Now let me see if I can show this with my webcam here. Let me change cameras. Where's the mouse? Man, I wish you guys were in my room. So let's see how well we can see this. So if I strike it, see what happened to the water? Okay. Got sprayed everywhere. Okay. And if I don't know if you can see it, but as you look, oh, my hand was in the way. That was dumb. All right, let me try this again and try to keep my hand out of the way here. You got sprayed everywhere, right? And this is kind of fun because what happens is the tines of the fork vibrate back and forth. And my point of all this, I'm gonna get water away from computer keyboard. My point of all this is that sound, and this it doesn't even have to be necessarily. Yes, it is similar to those bowls that make sound, singing bowls or whatever those are called. I don't know. Okay. Yeah, and the water that flies around, right? Yeah, yes, you can do that with tweezers. Yeah, and I can also do it with there's some space here. Okay. I can also do this with a meter stick. All right, now moving my stuff over, I did bring a meter stick home. All right, let's see if I can aim this up a little bit. And I got a meter stick here. Okay. I don't know how easily you can hear that. That's kind of fun. Okay. All right, so a vibrating meter stick can do this. Okay. All right, so you can do that. Can you see that? So my the moral of the story here is that sound is created by vibrations. Okay. If you were doing experiments with a tuning fork, which I super wish you were, and I would ask you and you put it on your eyelash, and you put it on your earrings if you're wearing an earring, and it sounds like a doorbell. It's super fun. And then I would come back and I would ask you, what is the common theme of all this? If you had to pick one word, and that word is vibrations. Okay, so oh yes, that's right. So my point of all this is that sound is created by vibrating matter. Okay, sound is created by vibrating matter. All right, and as an example of this, okay, we can talk about a tuning fork. That's not really the sound that it makes, but I just wanted some sound effects. It actually sounds it's a very pure tone, a single tone. Okay. Now, how does it do this? It alternately compresses and then rarefies the air molecules. Okay. So as the time, and this is exaggerated for effect, but as the tines vibrate, you can actually see them if you put a tuning fork in a strobe light, you can see the vibrations. Or in front of an old, I don't know, well, never mind, they don't have them anymore. Old cathode ray tube TVs, but they don't have those anymore. So never mind about that. But you can see the vibration with a strobe light. And so these tines, they alternately compress and then rarefy the air molecules. What that means is that sound is a longitudinal wave. Okay? The air particles vibrate in the same direction, as the wave travels. Okay? In the same direction as the wave travels. Sound is a longitudinal wave or a compressional wave. Okay? Because the air particles and the direction that they vibrate and the direction that the wave travels in are the same. Okay? This sound presentation PowerPoint is not loaded onto Schoology basically because I forgot to load it. The class notes are, the PDF of the notes, but this is not, but I'll take care of that after class today. So if you want to check this thing out later, then you'll have access to it. Okay, here's a simulation as a sound wave travels through the air. You can see the compressions as they travel to the right. Now you might think that all the air particles that are shown, or all the simulated air particles that are shown, are going to end up on the right side of the screen. But that's not really what happens. You see them moving to the right, but they actually end up vibrating to the left. So as you can see, if you focus in on one of the particles, you will see it vibrate to the right and then back to the left. Okay, whereas the wave travels through. Okay. I heard a good analogy about this that made this analogy with traffic. If there's an accident on the side of the road on the freeway, you know, everybody stops to look at it, right? So if you think about a car, you know, if you were looking at before they got to the accident site, all the cars are spread out, right? But then the cars get up to the accident site and they all compress together. And then the cars make their way through that little bottleneck and they emerge on the other side and they speed up again. That's kind of what happens here. The particles end up, you know, getting compressed together, but then they end up spreading out again. Just like a car going, if you think of a series of accidents on the side of the road, you know, there'd be periodic bottlenecks as people slow down for rescue workers and to, you know, rubberneck and all that kind of stuff. Okay, so I heard an analogy. So if that works for you, then that's great. But the point is that the particles vibrate. They don't all just move down the line. Okay. Okay. A typical tuning fork, such as the one that I was holding, vibrates 320 times per second, creating 320 compressions and 320 rarefactions per second. That's typical. And if you're a musician, I think this is E. I believe, if I remember right, this is E on the musical scale. Okay, but I'll show you that a little bit later on. Okay, now, yeah, I wish I had my guitar, but I gave my guitar to my daughter, so I don't have a guitar anymore. And perhaps well, I'm going to have to eventually borrow a guitar from one of the music staff because I want to show you that. Not that I can't play. I know the theory. I just can't do it. I haven't practiced enough. Anyway, if we increase this to 3,200 times per second, would I be able to hear it? Is my eardrum sensitive to that? You know, if I increased it to 32,000, would I be able to hear that? You know, there is an upper end. There's an upper end to the range of frequencies that my ears, your ears, the human ear can absorb and pick up. There's also a lower end. Okay, so we have what's called, okay, so what did I say here? 320 waves per second are emitted. So wave has a frequency of 320 hertz. Yes, I didn't see Okay, all right. So, but there's a range, and we call this the audible range of humans. Okay, and we're not all created equal. Some people have better physical equipment than others, but on average, okay. You guys remember? I don't know if they did this, but I remember when I was in second grade, first or second grade, a nurse had headphones on me, and she said, "Raise your hand when you can hear this, and lower it when you can't." Did you guys do that? Did they ever test your hearing, like when you were a little kid? Yeah. Okay. They were testing your audible range, and actually, um, that was when my daughter was in like first grade. When my daughter was in first grade, that's when we found. That's when we found out that she couldn't hear through one of her ears. I think it was the left one, and because she had it all, she had drainage problems in her ears. She had to get tubes put in her ears to help the drainage. You know, but yeah. Anyway, that's when they test your hearing, and on average, this is the range of human ears from 20 hertz to 20,000 hertz on average. Okay, so you can hear as low as small a frequency of 20 hertz or all the way up to 20,000 hertz. Okay. Now, are there sounds that have a frequency lower than 20 hertz? Well, yes, we can't hear. And if they do, those are called infrasonic. Those are called infrasonic. Now, we can't hear them, but some animals can. Elephants can hear them. Okay? Elephants can hear them. Now, question for you. Question for you. Have you ever been in a concert and the woofer speakers are on the floor and it was so loud that you not only heard the music, you felt it? You felt it? The lower frequencies can actually cause our bodies to vibrate. Like our bodies can, if it's not too high, our bodies can actually absorb those frequencies. And these are also created by heavy machinery. Okay. And it has been thought, it has been theorized that if you stand next to a machine, a huge machine in a factory that's, say, stamping out metal pieces and going boom, 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 a super heavy machine, and you're standing right next to it for 8 hours a day, 50 weeks a year, for 30 some years, those waves created could shake something loose inside your body. They could be physiologically damaging. Okay, so I think they have protection for those workers now, for the infrasonic waves that are created by heavy machinery. All right, but elephants can detect them. You've heard stories that animals can detect earthquakes before humans can. I'm not sure if it's because of the infrasonic waves created or not. Okay. Now, sounds. What are sounds over 20,000 hertz called? What are frequencies greater than 20,000 hertz called? Anybody know? Not supersonic, but we'll get to that. They're called ultrasonic. Okay. Oops. They're called ultrasonic. We cannot detect them, but dogs can. Okay. Dogs can. And they are used in some medical procedures. For example, they're used to break up kidney stones. If you have a kidney stone, which is like a calcium deposit in your kidney, and there's only one way to pass that, and that's by peeing it out, and it has to go through a really small opening, so it can be extremely uncomfortable. My sister had kidney stones. I'm knocking on wood because I have never had one. No, thank you very much. They're extremely painful because they have to come out through a very small opening. But they've said that ultrasonic signals can be used to break them up into smaller pieces, making them easier to pass. They're also used to detect a fetus in mommy's tummy. So I saw, using ultrasound, I saw my children in mommy's tummy before they were born, which was super cool, by the way. According to my research, dogs can hear up to 45,000 hertz, Whales can hear up to 100,000 hertz. Okay. Now I'm going to stop this. Stop sharing. I when I was walking in a hardware store one time, I got this dog training whistle. It was on an end cap in a hardware store, and I thought, oh wow, cool, ultrasonic whistle. I'm gonna buy this. You know, it was only like $5 or something like that. So I bought it, and here's what it sounds like. Wait a second, that doesn't sound like a whistle. Well, of course not, because if it is ultrasonic, you hear some things, but it's not the really high pitched ultrasonic. I think that's just for our benefit, so that's making some noise. But I sent this home one time with a person whose dad trained dogs for hunting, and I asked him, you know, test this out and let me know if it actually works. And they said, yeah, the dog responded to it. Okay. So these dog whistles, you know, actually worked, right? And then another time I was asking, I was going through and I was looking at this ultrasonic pest repeller, right? It's supposed to repel, you know, roaches, ants, mice, blah, 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 blah. So you're supposed to plug this thing in, and I don't know, drive them crazy. I don't know. Now, hold on just a minute. Okay, one of my cats is sleeping in a bedroom. I'm going to plug it in and see if it wakes up the cat. Should we do that? Yeah, sounds like fun. Come on. I like this cat, by the way, but that's okay. I can wake him up. So, hold on. I got to plug it in. Actually, that's just an extension cord. Oh, Mrs. Towers, can you help me here? Can you help me for a second here? I'm going to have Mrs. Towers help me with this. All right. I'm going to plug it in. Phil, hold on a second. Hi, Mrs. Towers. Say hi.
Hello.
Okay. I'm going to sneak up on the cat. Okay. Plug it in. Yeah. Lights on. Doesn't seem to affect the cat. I don't think the cat can hear it. I think this thing's a hunk of junk. Can you unplug it? Okay. All right. Thank you for helping. Yeah, I don't think that, at least the cat made absolutely no reaction. So I don't know if this thing works or not, but if I had to guess, I'd say not. Okay. That was fun to try anyway, though. Oh, wake up about another minute. Then one more thing. Deer alerts. Okay, these are like deer whistles. Okay, and I had this open, didn't I? I had this open. Now, yeah, they look like this. Come on, I do this quickly. We're running out of time. So they look like this. It's a hole in this end, and then a little itty bitty hole in the other end. Right, and the wind. You put these on the underside of your car, and the idea is if you go over like 35 miles an hour, the wind passing through these creates an ultrasonic signal that are going to scare any deer in front of you off the road. Now, in Wisconsin, that's a very real concern because there are deer everywhere. And you really don't want to hit your car. You don't want to hit one to kill it. But on top of that, it's going to cost you $1,000 to fix your car, right? And yes, I have hit a deer, and I think my wife has hit 3. They're just everywhere. So you really don't want one hitting a car. So you put these on your car to prevent it. And I had these on one of my cars. Never hit a deer with that car, right? It hit deer with other cars that I forgot to put these on. But yeah, you don't have the deer in California. In Wisconsin, they're everywhere. So but you can put these in your car and create an ultrasonic signal. They're going to scare the deer out of the road, okay? Because you really don't want to kill a deer. but you're not going to kill the last one. Don't feel too bad, but it costs you a lot of money too. All right. So anyway, those are just some examples of ultrasonic stuff. All right. Kind of ran into the end of the period there. Okay, I'm going to stop there. Waves worksheet 1 was due Friday. That should be in. Waves worksheet 2 is going to be due at the end of the day Friday. On Thursday/Friday, we will continue on into our sound unit. Okay, but until then, class is done. I wish you the very best of rest of the Monday and tomorrow, and until I see you next time. Okay. All right. So long.
For the homework that was due Sunday,
Waves worksheet 1. Yep.
the worksheet one, yeah, I did draw for question number 9. For the superposition, I
Yeah.
did draw what they're supposed to look like when they were actually reach the middle, but I didn't draw it on the line, and I didn't draw it in the actual middle.
That's okay. That's
As long
okay.
as I have the shape.
Did you have the general shapes correct?
Yeah.
That's what I'm after. Okay.
All right.
That's what I'm after.
Thank you.
Yep.
Have a good day.
Yeah, you too. Jelini, what I was talking about was waves worksheet 1, which what I call don't make waves. And I went over the answers to that at the beginning of class today. All right. So you should get your submission to me. Waves worksheet 1. That's what it's called, but I want to be a little more imaginative, so I called it "Don't Make Waves," and that's yeah. Okay. Does that make sense? Okay.